Welcome everybody for our session tonight. We're giving it a few minutes before we start. So welcome to our Central St. Martin's Digital Innovation Season 2, Biology is Digital. Tonight is our very first event for this program, and there will be talks every Tuesday for the next 6 weeks. With this program, we want to explore the intersection between technology and ecology. And so we have a lecture series which is open to all, as well as a series of digital workshops which will be reserved to Central St. Martin students. Our workshops will be including machine learning, creative coding, 3D modeling, generative arts, electronics, robotics, eco-web design, and various digital tools that can help us understand better natural systems, assess them, work with them, so that we can engage equipped with real tools in terms of ecology. You can look at the chat in the link in the chat if you want to book further events. Tonight, we will be exploring the role of data in the ecological crisis. We will be looking at how nature impacts technology and how technology impacts nature. We're in the midst of an ecological emergency. We know that, and it's been highlighted yet again by the latest IPCC report, which was published a couple of weeks ago. The time to act is now. So how do we, artists, designers, architects, creatives, how can we learn from other disciplines to intersect our creativity with planetary science? So tonight we're hosting a range of non-scientists as well as non-creatives as well as creatives, but we're hosting a scientist who is based in the Amazon forest and who will tell us about the use of data in tracking deforestation. We are welcoming an engineer who is based in the Arctic and who will tell us about data and how to use data to track biodiversity. And finally, we're welcoming an artist who is working with climate data and pursuing a PhD in that field. So please use the chat in the YouTube chat to ask your questions. For those of you who are in our lecture theatre, we will be asking you to simply ask your questions, and Elsa will be repeating them to us. Please keep your cameras and microphones off, and please note that this session is recorded. So first of all, let's welcome Dr. Erika Beranger. Erika is a senior associate researcher at the Ecosystems Lab at Oxford University. She's also the co-leader of a working group at the UN Science Panel for the Amazon. And Erika is from Brazil. She works in a joint Brazil-UK research consortium, and she's researching deforestation in the Amazon, forest ecosystems, and forest climate resilience. So Erika, the screen is yours.
Thank you very much, Carol. And it's going to be a bit of a challenge to speak to a different audience than what I'm used to, but that's actually where the real pleasure comes from, is to bring the joy of working in the Amazon and what's really behind the curtain of working in the Amazon to everyone. So I'm going to share my screen, which I hope it goes right. Again, let me just see. Yes, I think you can see my screen.
Yeah. Yes, it's perfect. Yes. Thank you.
Okay, perfect. So today we're discussing the role of data in the ecological crisis. I'm not going to bring the focus to the Amazon, because we hear so much about the Amazon all the time. And usually it's quite a binary discussion. We hear about, how do I pass my slides? Yeah. we hear about this luxurious green forest, which is full of mystery, so full of biodiversity. It's estimated that just in the Amazon, we have 16,000 species of trees, without counting the part of the Amazon that goes up the Andes. That in an area that is the size of a football pitch, we have more species of trees than in the whole of the UK. There's so much to be discovered. Just a couple of years ago, a different species of river dolphin was found, was described by science, and every year dozens of species of insects and spiders are described by science. The same goes for plants and fungi. But the other way that we discuss the Amazon in this binary approach is this: the Amazon that doesn't exist anymore, the Amazon that is gone and it's being converted into agribusiness. But how do we know that? When we discuss the Amazon lost X amount of square kilometers this year, or the Amazon has lost an area the size of Wales, 3 size of Wales, what are we really talking about? Well, these are the actual numbers. What we have this area in green and yellow is the area of the Amazon biome. What is the actual Amazon forest, which occupies 9 countries. So Brazil, where I'm from, Bolivia, Colombia, Peru, Ecuador, Venezuela, Guyana, Suriname, and French Guyana. And in yellow or orange, depending how this is appearing on the screen, we have the areas that have been lost till 2017. The areas that have been completely chopped down, that were originally forests and are not anymore. In total, we have lost 14% of the Amazon biome, which is equivalent to about 3.5 times the area of the UK, in about 800,000 square kilometers. And what I'm talking about is the loss of primary forests. Those are forests that never been clear cut before, never been felled before, that has been existing there for thousands and thousands and thousands of years. Another important data that we have is that most deforested lands have been converted to be pastures, to become pastures. And this is really important to emphasize, because most people think, well, that we are turning the whole Amazon into soy field. Yes, croplands are an important driver, an important cause of deforestation, but most of the deforested areas, the main driver of deforestation is for beef. Brazil is the largest beef exporter in the whole world. And another important data is that 29% of the areas that have already been deforested are occupied by secondary forests. So secondary forests are those that are regrowing in areas that have been completely deforested before. So that's the forest recovering. It's not reforestation, because reforestation implies an active action. So humans planting forests, it's not that. Secondary forests are just naturally regrowing in those soils. And those secondary forests, although extremely important to preserve biodiversity, they are structurally and biologically different than primary forests, which are the ones that I initially mentioned, or old growth forests, or pristine forests, as we hear in David Attenborough's documentary styles. Those secondary forests, they are shorter, have fewer species of both fauna and flora, fewer interactions between these species, store less carbon, sequester less CO2 from the atmosphere. Still, they are super important because they are still a very important tool in combating climate change, as they are sequestering CO2 from the atmosphere and storing in the trunks of the trees. They're just less important than primary forests. So the main conservation objective should be to maintain those primary forests rather than just maintaining second. We should never deforest primary forests. But how do we do that? For that, the first step would be to know where deforestation is happening. That is crucial to develop more targeted, more effective public policies to combat deforestation. So I have 2 graphs here. On the A, on your left side, you have area in the 10,000 square of kilometers, the scale. And in the B, or the right side graph, we have percentage deforestation of primary forests, according to this paper that came out in 2021. In dark blue, we have countries. We can see that Brazil is by far the country that deforested the most across the Amazon biome. It has deforested way more than all the other 8 countries put together. And in the light blue bars, we can see deforestation in Amazonian states. So Brazil is divided like the United States. It has, like the United States of America, it has states like, for example, you have Texas, you have New York, you have Ohio. In Brazil, you have states. 9 of them are in the Amazon region, and those are the ones listed over there, like Amazonas, Pará, Mato Grosso, Rondônia, Roraima, Acre, Amapá, Maranhão, and Tocantins. And Tocantins, sorry, I spoke in Portuguese. So those states, we can map which of them are deforesting more or less. If we look at Pará, which is the second from top to bottom, the second light blue bar, we can see that it deforested more than all Amazonian countries put together. So just one Brazilian state has deforested more than all these Amazonian countries put together. Okay, this is a very big state. It's about 10 times, or no, I think it's about between 8 to 10 times the size of the UK. So it's a huge, huge, huge state. But still, it has deforested more than all the other Amazonian countries put together. This is really important, because when you talk about international agreements to preserve the forest or combat deforestation, we can see, well, maybe we should focus in Brazil. Brazil is a country that is losing so much primary forest as opposed to Ecuador or as opposed to Suriname. So maybe international agreements should focus in Brazil, both in terms of benefits for keeping the forest standing, but also in terms of punishment for commodities coming from newly deforested areas. And the same goes for Brazilian states. If we think about national laws or national rules within Brazil, we can target those policies, those rules towards the states that deforest more. And actually, that's what happened back in 2008 and 2009, when deforestation was going down in Brazil, was because of those targeted deforestation policies, what you call command and control policies, which is look after where the largest deforestations are happening and try and stop them almost in real time. So it's crucial to know where deforestation is happening, especially because we are talking about an area. If you talk about the whole of the Amazon, is an area that is it's about 60% the area of Europe. So it's impossible to have a lot of environmental police looking around and seeing what has been deforested or not. But also it's important to know when deforestation is happening, because if deforestation is increasing, and here in this graph, also from the same paper from Charlotte Smith and collaborators from 2021, we can see that the peak of deforestation was happening in the early 2000s and then has gone down up to 2012, which then started increasing again. And since 2019, which is not being shown in this graph, you start a sharp increase in deforestation. And that's really important, because if we know that deforestation is decreasing, we know that rules are actually being effective on the ground. While if deforestation is increasing, it's a sign that we need to change the rules. We need to change both the punishment and the benefits, the carrots and the sticks that are being offered for people on the ground behind deforestation. And it's also really important to talk about secondary forests that I mentioned in that first slide about the numbers. Because if we have 29% of the areas that have been deforested in the past of the Amazon regrowing as forests, well, do we want to preserve those secondary forests? Should we cut them? Should we put them back into production? Should we leave them as forests? What is their role? And that's largely dependent on the age of those forests. because the older a secondary forest is, the more carbon it will have stored in the forest, the more species of plants and animals, the more ecosystem services it will provide for humanity. So it's important to map both where they are and how much they are growing every year, how their area is expanding or decreasing this year by year, which we call the secondary forest dynamics, and how old these forests are. But how do we get to all this on how much the Amazon has been deforested, how much is regrowing, when is regrowing, when is being chopped? Well, all this is being done by a lot of different research groups, and especially in the past 5 years, it's been growing with Mapiomas. Mapiomas is a Brazilian initiative, which is a combination of both researchers from universities and NGOs that analyze satellite data between 85 and 2020. So it's basically 35 years or 36 years worth of data that you can both map and quantify deforestation and regeneration of the Amazon. And you do this through algorithms that are able to detect whether a pixel, and this uses freely available satellite data from Landsat, from NASA, and detects whether a pixel is either forest or not forest. So it's a binary analysis, and whether a pixel that is forest in year 85, in year 87 becomes non-forest, and then in years 95 becomes forested again, so you know that secondary forest growing. But then you can know that in year 97, that secondary forest was cut. So all these very complicated and detailed dynamics that is essential to know how much we are emitting in terms of CO2, how much biodiversity we are losing, or how much we are sequestering in terms of CO2, and how much biodiversity we are conserving, we are preserving. This all comes from analysis like this, done by Mapiomas, which uses extremely large data sets. The pixel sizes are 30 by 30 meters. They are in total 900 square meters. It's a lot of data. So we need to train a number of algorithms and have very skilled data science to be able to do that. That is a technology that was actually developed first by Brazil in the early 90s. To track deforestation in the Amazon. This technology has been exported for free to quite a few African governments in the Congo Basin to be able to track deforestation in the Congo Basin as well. But that would be impossible without free satellite data, large data analysis, the skills to do that, the servers to do that, and quite a few dedicated data scientists. And all of this put together can influence public policy, like my research group did in 2020 in this new law from the state of Pará, that one that is deforested the most in the Brazilian Amazon, and which started a new law called the Amazon Now Plan. This is a free translation. And what this plan does is to try to map what are the areas that should be prioritized for regeneration, for secondary forest regrowth, and how much CO2 could be sequestered by those forests. But all this would be impossible without years and years and years of work of all those data scientists mapping where and when primary forests are being chopped down, and where and when secondary forests are growing. And also, those algorithms now, they're able also to map if it's an area that's been deforested, is converted to pasture land or cropland, which again, it's essential if we want a targeted regeneration of secondary forests. Where we are gonna, what is the cheapest land to focus? It's gonna be a multi-million soy field operation or quite a non-profitable with small pasture. We can do all this with this large satellite data sets, which are becoming increasingly more detailed, with increasing resolution. Like, for example, the ones coming from Planet right now, which the resolution is a pixel size of 2 by 2 meters, which is amazing. That's smaller than a tree crown. There's also type of data that we can and should use. And when we discuss and research in the Amazon and conservation of Amazonia, including Amazonian biodiversity. One of them is camera traps. Camera traps are just cameras like that one that I'm trying to put in a tree and the other one hanging from my hand that you put on trees. You can leave them for weeks to months, depending on your battery capacity and depending on how much it breaks. It's a rainforest, everything breaks in the rainforest pretty quick. And you can map, for example, the occurrence of endangered species, like we did in this video here. I don't know if you can see. There's this animal on the right-hand side of your screen. It's approaching. And then you can see the big head of the jaguar. So we're able to map the occurrence of those endangered species like the jaguar. Oops, how'd they get out of this? Next slide. Yes. You can also map events of predation. We know very, very little about Amazonian biodiversity and about its interactions. It's very different than the UK that we have for centuries. Researchers, scientists, naturalists mapping biodiversity and what is eating what. We don't have that in Amazon, but we can do that with camera traps. Like in this case, that you're going to be able to see some eyes going up a tree and some eyes coming on the left side. And then you can see an ocelot, which is a smaller cat, preying on a skunk. So that's what we just saw on that video. An ocelot is about the size of a Labrador, let's say, more or less. Oh, not this. I want to go to the next one. Yes. We can also map frugivory. So the interactions between animals that eat fruit, and they are really important because those animals eating fruit, they're going to disperse those seeds. They are the engineers of the forest. They're going to carry seeds from point A to point B because they eat in point A, they poop in point B, and their feces is full of seeds. So this is what camera traps can also do, is to track those interactions. Like this agouti here, that is eating the fruit and is gonna eventually swallow the seed and poop it elsewhere. And things like frugivory is essential if we're talking about forest regeneration, because without animals, we don't have seeds arriving anywhere. And if we don't have those seeds, we won't have the forest regrowing. So it's really important to establish the interactions between the wildlife in the Amazon, because they are largely unknown, but they're crucial for restoring forests in the region. There's other things that we can use. For example, this is a Lycor. It's a CO2 chamber. So can you see there's a leaf inside being illuminated by some UV light illuminating the leaf? The leaf is stuck to that screen of that machine, and that machine is pumping a reference amount of CO2, a reference amount of light, and then we can measure how much each leaf is photosynthesizing, which by that I mean sequestering CO2 from the atmosphere, and how much is respiring, which is emitting CO2 to the atmosphere. And that helps us to establish the CO2 balance of the Amazon, which is essential if we want to know the role of tropical forests and help us mitigate climate change. A machine like that, and that can be used straight on the field, is very, very, very expensive. It costs about 25,000 to 30,000 pounds. And of course, you have to deal with a whole lot of export permits, research permits, etc. But it's essential to track CO2 balance of the forest. There's also things like audio recorders. This photo is not one of my photos. I couldn't find my own photos of audio recorders in the Amazon, which is something that we use. They're basically like camera traps. We set them up, and camera traps, they are activated by movement and by heat of animals. While audio recorders, you program them. For example, we have them set to record 10 seconds of every minute. We have terabytes and terabytes and terabytes of data. And with that, we can detect species occurrence, detect again endangered species that are vocalizing, because of course, if a species don't vocalize, we're not going to detect by audio. And we can identify new species. That's being used a lot by people studying amphibians, like frogs, to understand if a new species is there or not, because the vocalization of each species of frog is different. But there's some difficulties in all this. So for audio recorders, we have to create an audio library. That means that you have a library of all the sounds that occur in X place. Let's say here in Oxford, where I am, the amount of species that occur by the Thames here in Oxford. So you have the library and you run an algorithm which compares that library of yours to all your audios. However, the Amazon is not Oxford. It has over 2,500 species of birds, mammals, amphibians, many of which have not been described. So those libraries have not been developed yet. They are being developed as we speak. And that's a lot of work from data scientists and sound engineers. And there's also the interference of rain, insects, like if you ever heard cicadas, they are so loud that interfere with the sound, with understanding of hearing the sound of other species. There's also people talking, like hunters, that the sounds of gunshots, there's a sound of chainsaws, and all that interfere with detection of sound. So there's a lot of other challenges that I have skipped through a bit in my talk, which includes, for example, theft of all these recorders, but they have an enormous potential to be able for us to do long-term field work with less, with lower costs and lower time investments on the ground, although we still need people. And there's also the use of ecological data in art, which is something that I haven't seen much. I just videos.
Erica, yes? I'm sorry to interrupt. You've kind of gone over your time, so if you want to conclude shortly, that would be
I have one more slide. Yes.
Okay,
perfect. So the use of ecological data in art is something that I'm just putting here as a provocation, and there's a lot of art students, because it's something that I haven't seen much. I have showed just lots of videos and sounds, and we can think about immersive experience, for example. I haven't seen much of that. There's also the use of political data mining. So in Brazil, every law goes through this massive website every day with thousands of pages, and you can data mine that massive website to see laws that are changing and impacting the environment and the conservation of the Amazon. But one thing that is essential for all this is people, which is what I said before. People are the ones ground truthing the data that are being sampled remotely, sampling the data on the ground, doing the maintenance of equipment. And we all had our fair share of near-death events, like tree falling on top of our cars, for example, we're crushing our cars, snake bites, scorpion bites, weird insect bites that develop tons of allergies, diseases that are undescribed by medicine, and the occasional violence on the ground, because we are working deforestation frontiers. So it's vital to consider the people on the ground during the work. We want to collaborate, want to share data, but it's very important to think about the people that are putting their life at risk to get all this data. Thank you very much.
This is brilliant, Erica, and great to have all the data, but also to look at all the tools you're using. Really interesting to see that. We're going to take questions at the end after our three speakers, so we'll move straight to our next speaker. But please pop your questions in the chat if you have any, so that we can move straight into the Q&A after the third speaker. So next, we would love to welcome Dr. Shridhar Jawak. Shridhar is a senior advisor at the Svalbard Integrated Arctic Earth Observing System. He's a specialist of Earth observation in the polar regions, and he has worked in the Antarctica, in the Himalayas, and he collaborates with space agencies to calibrate satellite missions. So, Shridhar, the screen is yours.
Thank you, and let me share my screen. And hopefully you're able to see the full screen mode now.
Yes, all good.
Okay, so thank you for the introduction and invitation for this interesting webinar in front of the diverse audience. And it's my really pleasure to speak to this diverse audience. It was really difficult for me to make the presentation, but I'm making this presentation in best of my capability. So I would specifically focus on Earth observation satellites and the data to monitor polar regions. But this is more of a generic title, but I would specifically focus on how to monitor polar animals and the plants. But before going to this presentation, I would give you a brief introduction to what is remote sensing and how do you use the remote sensing data and why do you need the remote sensing data. And then I would go to the main topic of this today's webinar. And I think I would start from the Erica's talk. She has shown a beautiful map of Amazon. Not beautiful because it's deforestation, but that is kind of a thing you can do with the satellites. And the similar thing I can show you in the polar regions. So before I go to the what is today's topic is that, but I represent the SIOS, which is the Norwegian initiated international collaboration to create the regional observing system. And the main important thing about this observation system is that open, free, and harmonized data from both from in situ measurements or the ground measurements and also from the satellite data. And it has the regional scope, that is Svalbard. And it is also a consortium of the institutions. We have 28 institutions from 10 countries, and we focus on the processes and Earth system sciences like environmental and climate change issues. And if you are more interested in which countries and which institutions, here are the logos. And since this video is being recorded, you can see also again about these institutions. But just typically to give the statistics, around 20 Nordic members or 7 European members and 3 Asian members into this consortium. And as I said, that we focus on integration, both satellite-based data and in situ data. The dots on the Svalbard shows the in situ measurements, and the satellite data gives you images, and or not only images but also other kind of data sets, and that can be integrated to give the comprehensive picture of the Svalbard. And that is what our aim to do for the long-term measurements in Svalbard. So this is basic information about what we do. But now I start about why remote sensing or why we do it in Svalbard. So I'm based in Svalbard in Longyearbyen. This is my office, which is shown with the arrow, which is very strategic position. It's next to the cantina, and that's why it's very strategic. But here you can see it's not real yesterday. This image was captured a couple of months back, but this was captured when I was going for a walk in the office, and then this is yesterday, and this is today. So you can see that these are changes, rapid changes you can see in Svalbard going on. And not only in Svalbard, but in Arctic. But Svalbard is warming greater than is warming faster than any other place on the planet. So such kind of changes happening in Svalbard can be only tracked with the satellites or Earth observation data sets. And this is why I showed this picture, what is the importance of the frequent data sets in Svalbard. But for those who really don't know much about satellites or Earth observation and the other kind of remote sensing, I generally ask these questions. In this webinar, I think we cannot have interactive session, but I generally ask questions. Do you capture selfies? And if, of course, you capture, everyone captures selfies, but how many? And how many is important, but more than that, it's do you capture selfies at regular intervals? And what is the resolution of your picture? Of course, it depends on sensor, or it depends on your phone. And this is what we do, or what I do is process the satellite data. The satellite data or the photos are the Earth selfies. And it's a very simplified version. Not all the satellites give you the selfies or the photographs, but today I'm speaking more on those who are giving you photographs. So our space is very busy, and we have many satellites in the space. And this is the picture from ESA. And by by now we have launched around 12,000 satellites, and out of that, around 7,300 are active now. And year 2020 was really special because it's the highest number of satellites were launched, like it was around 1,300. And in year 2021, we launched around 850 satellites. But out of that, how many are the selfies satellite or Earth observation satellite? Are only 906, and the rest of the satellites are different purposes like communication or just to do a navigation and positioning, like you have a GPS. But the overview of this high resolution remote sensing systems, or I think Erica mentioned about Planet, but I'm giving you the picture, the graph, how it is improved from 1998 to 2018, and now it's still developing. So this all started in something around 2000, and where the QuickBird was launched, and then different satellites being launched. That gives the resolution. You can see on the x-axis 3 meter, 0 to 3 meter, around 0.5 to 3 meter resolution. And in the other graph, you can see the general information about the different kinds of satellite. I think Erica also mentioned about Landsat that was launched somewhere around 1970 to 80s, and then we have many satellites. So this is a general overview of how satellites and Earth observing satellites are growing since like many decades now. But what is remote sensing for those artists sitting out there? It's simple. In a textbook language definition is an art of acquiring information of an object or the phenomenon, and without getting into the direct contact with it. But in technical terms, satellites collect information that transfer the data from different parts of the electromagnetic spectrum, and that provides researchers like us with enough information to monitor trends of natural long and short-term phenomena. And remote sensing makes it possible to collect the data, dangerous or inaccessible areas like polar regions, one of them. And here the picture shows that how do we monitor or count polar bears in the satellite. But remote sensing can be many things. It can be satellite or rockets that gives information, manned aircraft, unmanned aircraft, or locally guided drones, or the fixed measurements giving the on the ground, like camera traps Erica has shown. So such kind of images are also called as remote sensing on the ground based. But today I'm focusing more on the Earth observation rather than other kinds of remote sensing. And why remote sensing in polar region? The picture says more than the text, but the high logistics cost to go to the Antarctica or the Arctic to conduct the field work, and also it's impossible to conduct the continuous monitoring, and that's why Earth observation data provides the data. Earth observation provides the data about these polar regions and gives this synoptic coverage and the temporal images, and this is why we need remote sensing. And this is the picture we made during last 2 years, the effect of pandemics in the Svalbard. So because of this pandemic, most of the scientists couldn't visit Svalbard and carry out the field work. And during this, the denied access to the Svalbard regions, the only solution was to get the data from the Earth observation. And this is why remote sensing is important. And as I said, multi-temporal images. Here you can see how we get the images every after 5 to 6 days. This is the Longyearbyen town from this space, and here what I can't show the pointer, but the bright pixels, they shows the infrastructure here, and the greenish part in the ocean, that's more of the phytoplankton and the chlorophyll, and then you can also see sediments into changing sediments using the satellite data. But also why it is important, scientists are collecting in situ data or the ground data from the fjord. Here you can see on the left side, the dots shows that the chlorophyll concentration, which are collected by the scientists by the instrumentation. And on the right-hand side, you can see images of the fjord and showing the changes in the chlorophyll concentrations and the and also sedimentation. And on the left-hand side, again, you can see the changes in the chlorophyll concentration based on the scale here. So you can integrate both these data sets to get the clear picture of what is happening and how reliable your measurements are from satellites. Another reason about why remote sensing, this is the scientists digging the snow pit in the Antarctica, and why we need remote sensing or the Earth observation is that we don't want to take many snow pits. We need a technology to get the data remotely, but this is not possible thoroughly. We need in situ data, and in addition to that, we need Earth observation data. This is why the picture on the right shows we are trying to integrate or patch up the data. There are gaps in the in situ data sets, and to patch up this data with the remote sensing or the Earth observation. And also, the important information is that sometimes satellite data is the only way to achieve some information from the polar regions. And it is environmentally friendly because it doesn't cost the environmental footprint of the scientific measurements in the polar regions. And Svalbard, for instance, has among the best available infrastructure for making the calibration and validation of these products with the space agencies attractive. But now it's why remote sensing, what is remote sensing? But I would go through again back to the artistic perspective about remote sensing. So what is remote sensing versus clairvoyance? The clairvoyance is the extrasensory perception. You can access the information without touching it or without known senses. But the clairvoyance, I'm not speaking about the clairvoyance here. I'm speaking about remote sensing. But what does an artist and a clairvoyant have in common? The answer is that they both are great remote sensing experts. And the artists use colors, so do we. We use bands or spectral bands from the electromagnetic spectrum. And here I speak more about the visible spectrum or the infrared spectrum. I will speak more on the applications of this. So with this basic information, for 10 minutes, I just spoke on to give what is remote sensing, why remote sensing, and what we use, and what is the relation of this remote sensing with the artist. Now I would go to the specific application, how to monitor polar animals and the plants in polar regions using satellite. So satellite can be used for monitoring polar regions, including changes in glaciers, ice sheet, calving of icebergs, changes in the weather patterns, monitoring cyclones, changes in snow patterns, and many more. But in this talk, I would only focus on animals and plants. And the thing is that many satellite-based studies about polar animals include these questions. How many are there? Do the number change? And where do they go? Or if they leave, do they come back at the same place? And this is why I call it as imagination. It's more about how you imagine a satellite image and how do you use it for mapping the polar animals or the monitoring polar animals. So I would start from the first application, monitoring penguins from the space. And this is the research from Fretwell et al. And the Fretwell and Trathon in 2020 and 2012. And they use the very high resolution satellite data. The first image shows that this is published in 2012, and the red spots shows those colonies of the penguins with no previous population estimates in Antarctica until 2012. And that's what you can see, that how remote sensing is used to get these numbers. And here you can see what are the numbers of emperor penguin colonies in 2009, and the size of the circle relates to the estimated numbers of the pairs in each colony using the satellite data. But this research is also again revised in 2020. You can see the newly discovered or rediscovered, we say rediscovered, which were there and rediscovered with the satellite data using the Sentinel data sets. And this newly discovered red circles and the rediscovered yellow circles in relation to the previously known colony locations, like green triangles. These are the previously known triangles. And the dark blue triangles are thought to be no longer extant. So such kind of estimates we can do, we can find out the new colonies or newly discovered colonies using the satellite data. But how do we do that? Here you can see the satellite picture. This is a quick bird image, and it shows the penguins were visible as black dots and on the white sea ice. And also the newly discovered 11 colonies, as I shown in the past figure, you can see that emperor penguin colonies. And this is the example of the color corrected imagery from the Sentinel-2 satellite, and with a particular scale. And the arrows, you can see these are the pictures. You can see not on, this is not the best way to see that, but if you zoom it more and you can see the brown dots guano or the penguin pup, and on that background you can see the penguin black dots. But how do we do that? So here is as I said, this is the brown colored pixels and the black dots. The brown colored pixel is the poop or the penguin shit, and you can see it, zoom in and can see that the black dots as the penguins. And you can see it better when you process it, or you can process it with this is called pan sharpen, but I wouldn't go into the detail into this, but this is the image processing technique where you can see the penguins are highlighted, and then you count it with the automated algorithms to get this penguin pairs or the number of penguins in the colony. And this is another example of how did they do the mapping of or the monitoring, counting the penguins using the satellite data. But why do you think it's important to count the penguins? So this is the image. What is much important from ecological perspective. So the colony distribution, size, and vulnerability, which is mapped, and that you can see that geographically all these newly discovered or the rediscovered colonies are in the regions that will become extinct or quasi-extinct by the end of this century under the current rates of carbon emissions. And this is why we count penguins using satellites. And this is necessary to do it again frequently. But from the penguins, let's go back to the Arctic. From Antarctic, we can go to the Arctic and also map the polar bears from the space, such as you can see these two pictures. And the right side, on the road, you can see no white dot, but in the left side, you can see the white dot here, or you can see the similar things here with the arrows, the yellow circles. You can see prominent white dots on the image A on the top, and on the image B, you can see these dots are not there. That means the polar bear, the animal, is moving. And you can see other arrows without yellow circles. These white dots are not moving. So these are the other structure than the animals. And here also you can see from the image on the top, A and B, you can see the dots, white dots moving. And on the C and D, on the bottom images, you can see that these are the problems we face, like clouds and the water conditions, and that shows the bright pixels on the images. And this is why this is still under development to find out the polar bears from the space. Then from the Antarctica to the Arctic, and then we go to the ocean, we can also find out the southern right whales. This is also an attempt from British Antarctic Survey, Fretwell et al. Here on the graph, you can see on the right is the submerged whale, and the left-hand side, the whales on the surface. And here, I only want to show that the signal from the satellite sensors show the peak signals when there is a whale in the ocean. And this is what we use for counting whales from the space. And it's how do we know that it's a whale? Because it has the right size, like up to 16 meters long, and the object is in place where we would expect to find whales. And there are no other objects which can cause the errors. But here you can see the different images of these whales, and several of these images could be interpreted as whale pairs or as a mother and a calf. Others may be displaying behaviors such as the tail slapping or rolling or the blowing. On several images, there is a strong return at one end of the feature, which is most likely the calyces on the whale's head. Also, you can say the spectral profile of the whales, different spectral bands. I mentioned about the spectral bands, and you can see the differences into the whales and the ocean. And you can also identify with your naked eyes on the 1 meter or 2 meter resolution images, and you can map them. And also you can do it by the algorithms, and you can compare them, the map with the manual digitized and the map with the algorithms. And there is a good match of this these two figures, and this is why the automatic algorithm saves a lot of time. And when you consider larger regions to find out the whales, it is important to get the automated ones than the manually digitized ones. So I spoke about the polar bears, penguins, and the whales, but you can also find out reindeer on the ground. But let me tell you, this is not a satellite imagery. This is aerial imagery, but of the around 30 centimeter resolution. And the similar images you can also get from the satellites for 50 centimeters, and still you can find out the reindeer in the Svalbard. And finally,
if I may interrupt, sorry, if you could conclude
yes,
the next minute or so, that would be great.
Yeah,
thank you.
Thank you. So that's my last few slides. So the Antarctic vegetation. So on Antarctica, I mapped the vegetation, which is only 1% of Antarctica, and it looks like a very sparse vegetation on the ground. And this is the first use of satellite data to give you estimates of the vegetation in Larsman Hills and the Shimaka Oasis on the eastern Antarctica, but you can do this into other parts of Antarctica. But this is just to show that it is possible to map the vegetation, not only in Antarctica, but also in Svalbard. Like these 3 regions, you can see the images, and also you can see the 3D perspective of these regions to just better understand the distribution of the vegetation. And not only that, but you can also see the onset of the vegetation in using the satellite data and which date it started to grow. And these images are 4 different images of different years to see that what are the changes into the vegetation. So with this plants and animals, I conclude my talk with the ground-based remote sensing, monitoring SCUA using the ground-based camera. So thank you so much for your attention, and I'm happy to take some questions at the end. Thank you.
Brilliant, thank you so much. Fascinating to see how you get such precision in the data with these technologies. So again, we'll take questions at the end. We'll now welcome our third and final speaker for the evening, Gaëtan Robillard. Gaëtan is a media artist and a visiting professor at University Gustave Eiffel in France. He's about to finish his PhD, so he's probably a little bit traumatized, I would assume. But thank you so much for making the time to join us at this critical time for your studies. But he's been studying the relationship between climatology and language. He's using a different type of data, language data, to study climate denial, which is more relevant than ever, I would say, particularly when we can see how much data we have, we know the science, but we see very little action following. So Gaëtan will talk to us about some of his research. He's been designing an installation using machine learning to display this data, and he'll tell us a bit more about it right now. Thank you so much, Gaëtan.
Thank you very much. Thank you very much for this introduction. I will just take a second to share my screen here so everybody can see a few pictures. Yeah, so I'm gonna just start this, and yeah. So I think you should see my screen now if there's any issue.
It's all good. Yeah.
Okay, thank you. So thank you very much for this invitation. Thank you to Central St. Martin's. I want to thank also the 2 previous presentation, the 2 researchers. This was really fantastic presentations. So thank you also for that. So I am a media artist and researcher, and my artworks are based on films and installations combining mathematics, climatology, and semiology. And I work often with interdisciplinary teams at the cross-border of art and science. Since a few years, I have started a PhD research on early computer art and also traces of algorithmic aesthetics in the contemporary world. And today I am presenting a project called Critical Climate Machine, which is supported by Media Futures, a European consortium that promotes data-driven innovations, both in the art sphere and in businesses. As we will see, Critical Climate Machine is mostly concerned with quantifying and revealing mechanisms of misinformation about climate change. So I will talk about climate discourse, machine learning, language, and more so how could we think of art, science, and data in regards to the mediation of climate. But first of all, I would like to introduce this presentation by talking a little bit about how I came to tackle scientific language and the image of climate change. So every work I produced is based on inquiries, especially into science. So climate change, algorithms, information, knowledge, well, describing the complexity of today's world is quite challenging. One of the forehead of information aesthetics in Europe, Abraham Moles, stated in 1968, information is now considered the third main entity of nature after matter and energy. So to understand the big changes we are facing in the biosphere and in the information sphere, it seems crucial to comprehend the role of data. Moreover, to be able to describe such a changing world, to describe this world demands also describing science at work, and I will try to explain. So in 2019, I started to investigate the way environmental change becomes visible through science artifacts. With the help of few laboratories and institutes in the north and west of France, I examined storm waves. Storm waves in the eyes of ocean science. Well, at the time, one of these institutes, which is called France Énergie Marine, which focuses on new energies, was especially working on different types of data collected during heavy storm events. 2013-14 winter storms in Europe were a series of events affecting areas of Atlantic Europe and beyond. And these years were also described by climatologists as exceptionally warm years. So it appeared to me that these data had something special to say. Jean-François, the researcher, and his team shared with me data and especially an algorithm they were using to study the quality of sea states. And there, I discovered that storm waves are seen as probable events in large time and space scales. So they come to our knowledge through the collection of statistical data and the computation of generative algorithm, which is an imaging methodology that is quite analogous to some of the early computer art pieces. So what is it that we face when science presents us such a world undergoing radical changes? The Wave in the Matrix is an installation I made with wood and copper, and that examines the evolution of storm waves. From oceanographic data, the work materializes in a network of surfaces the distribution of such a wave field. The network of processors makes visible a flow of mathematical operations, which in turn generates a swell of numbers. And as the processors gradually become out of sync, the display finally shows the heat exchange of the installation with the exhibition environment. The investigation into extreme waves and the transformation of the coastline then takes shape in an electroacoustic performance that accompanies the installation. Scientific data and scientific language became strong topics of investigation for me. Later, more recently in 2020, I got interested in a controversy about the climate research units in United Kingdom. So in November 2009, when a selection of illegally hacked emails between climate scientists were published on the internet, a few suggestive quotes were seized upon by many, claiming global warming was all just a conspiracy. A number of independent inquiries have investigated the conduct of the scientists involved in the emails, like The Guardian, but also official UK reports, all have cleared the scientists of any wrongdoing. Since the ClimateGate scandal, orchestrated by conspiracy theorists, the scientific consensus on the anthropogenic origin of climate change has been marred by misleading claims in the media. Well, we could say disentangling scientific truth from skeptical arguments is becoming an important issue in the 21st century. So how, in the era of data and artificial intelligence, do we deal with misleading claims and false truth? And especially how data and its reading by algorithms impact our understanding of the contemporary world. But let's have a pause on these two words. I shouldn't continue without a disambiguation here. Misinformation can be differentiated from disinformation. According to the Global Disinformation Index, disinformation should be looked through the lens of adversarial narrative conflict where there is creation of risk and harm. On the other hand, misinformation is the encompassing notion of incorrect or misleading information presented as a fact. This can be intentional and or unintentional. Moreover, disinformation is a subset of misinformation. And what about data? Data is an interesting word. It's so short, yet so over-compassing. And as I will try to argue, while using data in an artistic and technological framework, the very meaning of this word should be also carefully thought. In fact, from a humanistic perspective, data is a construct. There is something such as authoring data. And there is something such as bias. And producing data is not neutral. Not only it involves technical operations and interpretative readings, but it also requires ethical considerations. Now I'm going to talk about the recent project, Critical Climate Machine, or patterns of it. So one question here I have is, to what extent does false information about climate circulate on the internet? How would it be possible to expose this flux while undoing its effects? Scientist John Cook, that I met and communicated with, is a cognitive scientist who dedicates his career to the study and the debunking of misinformation about climate change. He wrote that online low quality information is just as more likely to go viral as high quality information. And by researching in Cook's work, I also discovered that recent research in the field of cognitive sciences establishes new methods in technocognition, where artificial intelligence is used to assist misinformation detection. And critical climate change as a project is largely informed by this approach. It develops machine learning strategies to investigate misleading claims about climate change. It is worth noticing that research in such direction is informed by historical data, and observation are covering 20 years time span in the case of this paper, and which is at the basis of the project. So I must also insist that the scientific work is concerned with data collected from prominent American conservative think tanks and contrarian blocs. And these organizations are established in disseminating climate skeptic discourse, and they are often linked to lobbies from the fuel industries. So I asked, to what extent does false information about climate circulates on the internet? Social networks is hot information. It moves all the time. It's fast. And the machine I am presenting here operates in two ways. It has a function. It classifies Twitter's data that is collected in real time. It also displays its own processes. And by showing what it is doing, the machine displaces a scientific object and investigates it in details. And I believe that revealing the processes that lead to the production of data and its analysis relies on an effort to clarify what is data and what is natural language processing. In addition, and as we will see later, a sound piece with voices also constitutes the work, highlighting education on disinformation, about disinformation, and language on climate change. The software collects tweets from 44 skeptical accounts linked to American conservative think tanks and lobbies. And on top of the query, a list of 91 keywords are used to filter the research with keywords such as Antarctica, IPCC, or fossil fuel. And all the tweets are accumulated in a database. In a time loop, the most recent 1,000 tweets are distributed as new inputs and spatialized in the sculpture. And the network of processors predicts, classifies, and displays labels of misleading claims on the fly. So what you see here being numbered is typical known and known misleading claims that are labeled. So the sculptor first transforms each tweet into a quantity of numbers, and then with the trained algorithm, it computes the probability for each tweet to belong to encoded labels. The distributed data stream runs through each unit of the sculpture and it updates until it stabilizes. And as a result, the visual output of the installation becomes a landscape of error codes, so to speak, which are in fact labels of indexes. Labels indexes, sorry. The audience is invited to map the misleading claims to the detected misleading tweets with the help of a code sheet. And the outputs are also returned to the database where each tweet is stored with its new label. It's important to say no text is displayed by the machine. However, by showing sequences of numbers and label indexes, the machine manifests the statistical nature of its operation. And the algorithm cannot interpret text by its literary meaning, not at all. But instead, it quantifies relationships between words and classes according to word frequencies. So by showing a part of the algorithmic process, the sculpture takes on the value of a signal, but this is far from being the sole outcome. During the process, words not only become digits, but they also turn into hits. Based on a grid of colors, a visualization witnesses the thermal evolution of the sculpture parts. It relies both on temperature variation and the amount of detected misinformation at a given time. The warmer the installation and the higher the number of misinformation, the warmer the color tones. Through visualization, the ecological and social implications of natural language processing are highlighted. Color gradients signal the physical impacts of computational processes, and eventually the way misinformation, but also big data, affects our social lives in unexpected ways. I would argue that in addition to the public experience through exhibitions, the accumulation of online climate misinformation in a database opens up new critical knowledge in the media field. And also the software code is currently under reviewing process with the Intelligent Museum and Health Lab at ZKM in Karlsruhe. Publishing also the Twitter data, the new Twitter data that is collected is in progress. And I want to underline that this involves working with Media Futures Network, King's College London, and the Eurocat Technological Center in Catalonia in Spain. So Critical Climate Machine comes also with a sound piece, and the sound installation is based on voice and dialogues, opposing climate skeptics and climate advocates. Misleading claims are refuted with the help of scientific knowledge. The voices that are constituting the dialogues were written and recorded on the basis of a workshop with high school and university students from a diversity of backgrounds and focusing on misinformation about climate change. The workshop took advantage of the refutation game, a card game that we specifically designed for the project. And the cards are based on systematic refutation of skeptical arguments. Well, this in turn facilitates a structured debate among participants. And the workshop is divided in 3 stages: a playtime with the cards in groups of 4 to 6 people, and a construction phase in duos, and also a recording stage. Based on the 2 workshop sessions, a final set of 34 short dialogues were then written for the installation. They were performed by 6 voices from students who already volunteered in the workshop. And at a later stage, I worked on the musical interpretation of the dialogues with IRCAM, a public research center in France dedicated to both musical expression and scientific research. I wanted to make a test on the dialogues against automation. Therefore, I asked Jérôme Nica, a fellow researcher in this institute, how the dialogue sound could be heard from the perspective of an algorithm which is programmed to improvise music. Our aim was to create a tension between embodied speech and generative speech. In the final work, the nature of climate semiotics emerges both through contradictory debates and through compositional operations conducted using a machinic and musical interpretation. So these interpretations were then edited and specialized in eight-speaker musical composition. And the more voices are modified by the generative process, the larger they become in the sound space. As a result, the audience experiences a movement between ordered meaning and unstructured language, revealing together computational processes and the nature of discourse and climates, its lexicon, its technicality, its repetitions. As an ensemble, Critical Climate Machine exposes mechanisms of climate misinformation. And I want to conclude that if in the cognitive sciences, computational logics help in the discernment of truth, musical research here opens to the exploration of norms that presuppose the mediation of climate through frameworks and formats. And we should question this. In functional terms, the installation collects and classifies new data from the climato-skeptic discourse flowing from Twitter. It leads to consideration on sharing the new data in open frameworks and contributing to knowledge on and about misinformation on climate change. In critical terms, the work displays a flux of data within its various states. And so how should we think of data now? As stated earlier, data is not neutral. Joanna Drucker, an academic in the field of digital humanities, has proposed a quite interesting terminology. She proposes the term capta versus data. The term capta is used by Drucker to point to extraction of phenomena and to acknowledge the act through which information is produced. Take, for instance, the position of the observer or the parameters with which information is collected. Producing data is an intellectual act, and revealing this is, of course, based on an ethical perspective. And I want to add here that examining the act of extraction also leads to looking more carefully at data from an ecological perspective. And I mustn't forget, and I must also credit all the teamwork, all the team effort that is behind this project. Jérôme Nica, Tony Uzio, Dionysos, Papa Nicolau, Vincent Nozick, Özlem Sulak, Laurine Capdeville, Jolane Goulin, who brought lots of work and lots of thinking in this project. So thank you very much. I'll be happy to take any questions later on. Thank you.
Brilliant. Thank you so much. What a phenomenal set of talks, really inspirational. Can I remind our audience, if you want to ask any questions, please pop it in the chat in your YouTube channel. We have the next 15 minutes for Q&A. And I would like to start by asking two questions before I open the floor. Of course, tonight we're looking at very much the relationship between digital technology and ecology. The three of you rely on digital tech for your everyday, for your work. We've seen a whole set of different equipments with you, Erika, and same with you, Shridhar, and Gaëtan, you actually incorporate a whole set of tools as well. If I had to say, and I think, Erika, you hinted on some frustrations to do with things break in the Amazon, so maybe you've given the answer already, but if I had to ask, well, is there a tech or digital tech that's not there yet that would be really useful to you? You know, what would be your sort of dream digital tool or digital tech that would add to your research, whether it would add to efficiency, to reliability, to, you know, what would that tech look like? It's a bit of a tough question.
Yeah, it's a bit of a tough one, especially on the spot. But what ideally I would love to see, and it's not there yet, would be real-time. We already have near real-time alerts of deforestation that goes straight to the environmental agency in Brazil. We don't have that across the Amazon basin, across the 9 countries, which of course would be ideal, but the technology already exists. But what we don't have is a real-time monitoring of fires in the Amazon. And that's because the dynamic of fires in the Amazon is absolutely different than the dynamic of fires in other ecosystems like savannas and coastal forests in the US or Mediterranean forests. The Amazon has trees that go up to 60, 80 meters. In average, the canopy is about 30 to 40 meters high. And the fires are about 30 centimeters only in height. So it's very difficult for satellites to penetrate the several layers of that canopy to see those short fires. When we hear about fires in the Amazon, normally a fire is occurring in open areas that have been deforested, and we are just getting rid of all the biomass that have been felled, or fires occurring in pastures to restore pasture land. So a technology to detect in real time or near real time forest fires would be ideal, remembering that these forest fires are very short. So it's a different technology than what is already in place, like in California, for example, or in savannas worldwide.
Great. So if you have any digital tinkers out there in our audience, here's a good mission for you. Gaëtan, is there anything that you find, maybe it's a different version of Twitter, it's a different, what would be a digital asset that would help you communicate more around this notion of climate denial?
This is a broad question. I mean, of course, there's a lot of assets here on the shelf, so to speak, that like algorithms and libraries that you can use to analyze language or, we should never forget these are like statistical objects. They don't get on literary meaning really. So I think maybe it would be interesting to have digital assets that enable critical practice rather than enabling more productivity or more extraction. So I would rather tend to say it would be great and very interesting to create those critical tools as digital assets that would help the reading, for instance, of data, or more specifically discourse about climate. And yeah, that's what I would say.
Yeah, because how do we know whether information is true or false? What is truth? All of this. So that's a really good point. Getting some digital tools that are really focusing on criticality would be exciting. Okay, Shridhar, you've got access to satellites, drones, you've got the whole kit. But is there anything that's not out there yet that would really make a big difference to your work?
Yes, that's a good question. I mean, there are numerous satellites in this space. As I said, it's around 906 Earth observation satellites. But they are all developed for other applications like agriculture, forest, so that the sensors or the satellites are not built exclusively for the polar regions. So there are quite few numbers of satellites like ICESat and CRYSAT that gives the information about. They are specifically made for the polar regions. But I would like to have more satellites which are focused on Arctic and Antarctica or the polar regions in general to monitor the changes in the polar regions. And also the high resolution satellite data I showed is Big Bird or the planet data. These are not free or open data sets. They are expensive data sets. So I would like to have free and open Earth observation data for the polar regions. That would be my dream.
Yeah, thank you for that. And that relates to a question we had in the chat earlier on, which I think, Erica, you've answered. which is to do, can we access this data as open source? And I think sometimes it's private, and because it's very expensive to send a satellite, sometimes it's open source, sometimes it's not yet published, as Erica, you pointed out, because before you need to, you're funded to do your research, you get all this data, and then you can publish your data. But before you've published, you will not be sharing your data. So there's different sets. But if you have any open source library you want to point to, whether it's the audience or the speakers, maybe put that in the chat. It sounds like our audience is interested in finding out where they can grab that open source data. So actually, Shridhar, to go back to your point, I wasn't aware that we didn't have a constant monitoring. This is interesting, we talk about denial, but there's a lot of assumptions as well. I assumed because the Antarctic, both poles, melting is such a critical thing for us, I assumed there was much more tracking going on. And you're saying we don't have dedicated satellites to observe those regions.
Yes, I mean, there are different satellites which are made for the forestry, and they can be used for regions. My meaning was we don't have a dedicated satellite just focusing on the polar regions, and that would give the continuous and dense data sets. And now
I'm quite surprised by that, I have to say. Yeah, good point. Okay, so we talked a bit about the digital tech. I now want to ask questions a bit more tricky. In that, so both you, Erica and Shridhar, you operate in a scientific field. So you conduct your research projects, you find the funding for your project, you do your project, your field data, and then you publish in academic journals, which is a very limited set in terms of your audience. And it's a particular language. Not everybody can understand a scientific paper. This in turn informs policy making, informs the like of the IPCC report, this sort of very high level report. But then that leaves, the sort of everyday person who's maybe a skeptic, maybe convinced, but doesn't quite understand the whole planetary data and planetary emergency. So how could we turn this incredible scientific data into something that's more accessible for the sort of, everyday person who's not trained in science? And the same question for you, Gaëtan, because again, you are an artist, your work is exhibited in galleries, you probably publish papers too. So again, it's a very particular audience accessing. You have to go in that gallery. You have to want to engage with this. You probably already have an audience that's interested in this if they go and see this. So how do we, and I think a lot of people in the audience would be here, how do we go beyond our field of expertise to reach a broader audience? Because, we are in this critical planetary emergency. Yet, I don't see many people voting green, for instance. I'm looking at the French election that just happened. So we know there's a lot of, we are in a state of emergency. The data is there, the science is there, the artists, and there's a lot of artists now working with climate data. But it doesn't seem to translate into change. So how do we convince people? How do you talk to your family about what you do? How do you talk to your friends who are not interested in, who are not experts in your field? How can we take what you do beyond your sphere of influence?
From a scientific perspective, I think there's two structural changes that are needed. So first, when I graduate from university, I did my undergrad in Brazil, or my PhD here in the UK. When I finished, I never, ever had any training on communication. My sole training is in writing scientific papers. That's how I know how to talk, how to communicate, the logic on how to build those arguments and how to communicate them. That's the community that I was trained to talk to. I wasn't trained to talk to my mother or my best friend about the information that is generated based on the data that I sample. So there's one structural change was about changing undergrad and graduate courses to make scientists able to communicate to a broader audience. Although we need to understand that our main aim is to write a paper. But that's the other structural change that is needed, is from funding agencies. If the funding agency is just funding a paper, if that's the criteria that you are being evaluated upon, you don't have the resources to do a policy brief, to do a press release. As a Brazilian, I try to generate policy briefs both in Portuguese and English, but the universities that I work with in Brazil, they might not have the infrastructure of a press officer, a press office at all to distribute those press releases. So how do you contact the Brazilian press, for example? So we need a structural change from universities, which in the UK, they all have a huge press office, but we need that in the global south. It's crucial in my case, which I'm working with issues that are completely connected to the global south, and we need funding agencies across the world to directly request scientists to have a communication or an impact pathway. Those things were requested by the Natural Environment Research Council here in the UK, and they are not, they stopped being requested from this round funding. So we need structural changes.
Great, really, really good points. Shridhar, is there anything you want to add to that coming from the same scientific perspective?
Yes, I think there were a couple of questions, and I think Erika has focused on one. So I would focus on another thing. How do we reach out the audience, those who do not know much about the remote sensing or the Earth observation? So one thing we do every year is to conduct a training course for the non-remote sensing experts who would like to use remote sensing into their regular projects. Like, for example, the field scientists who are coming to the Svalbard conducting the field, but they do not know about the satellites and would like to know. And such kind of training course, I can share for a few seconds my slide for the audience. If you can see, this is the training course we are conducting this September, AI for Svalbard, those who do not know anything about the AI and would like to use.
So hold on, because I think a lot of people in our audience might want to join that course. Is this open to anybody, artists, designers, scientists, or to scientists?
No, it's more open to the field scientist or the scientist who would like to use the AI, but they do not know about the AI. Okay. So this is the training course for this year we are conducting. Or if you would like to know about what are the Earth observation and remote sensing requirements for your research or the science, you can fill up this survey. Such kind of activity we do. And even after that, we have an active Twitter account. Every week we post the beautiful image about the Svalbard from the different sensors. So just to reach out the broader audience than only the scientists. So this is we generally do for reaching out those who do not know much about it. Yeah.
Thank you. And then Gaëtan, so how do you get out of the gallery space as an artist to communicate about climate denial?
This is a very good question. Thank you. And I could start with just by saying that, as an artist, it's never too much of a problem to change format or to question formats and how norms are working for a film or for a book or for a paint. So I think being versatile with formats and even making that a question in an artistic work is something very interesting and helps to actually to get an answer. And for instance, to be clear, for me, there's two ends somehow in like the way I get out of the gallery bubble. It's the education and the education. Well, I am lucky to be also a professor in the university. So this is like one ground, one field where the mediation of misinformation in a general sense, but also mostly about climate change is interesting to practice. So this is one side, and the refutation game that I mentioned is actually also a concrete answer in this direction. And the other end is working with science, and I think there's many very interesting initiatives in bridging maybe the closed world of hard sciences and the civilian society. And there's very interesting ways of thinking new cooperations, or so open data is one way, so that the civilian society can actually access, evaluate also the changes in the world, but also perhaps civic data, the way that we could eventually collect data from with the participation of many people. That's also, but to be very concrete here, I mean, publishing the data set that is being produced by the installation is a good work, to my mind, outside of the gallery. And it's a specific format where authorship also has a meaning somehow, or like it should be studied or assessed somehow, or yes.
So to follow up on that, there's a question from Jasper for you, asking, saying, great, interesting talk. Question for Gaëtan: did you investigate the impact of the art piece that you showcased tonight on visitors' behavior or interaction with climate change news? So do you actually evaluate the impact of the experience of your art piece?
There is something, there is a work, on an ongoing work in this direction. We worked with the Deutsches Museum at the beginning, who hosted a part of the work in a residency called the Intelligent Museum Residency. And the artificial intelligent aspect of the work was pushed forward, and questionnaires were proposed to a part of the public or in some time frame, and there's a work here. And actually we bridged Deutsches Museum, I bridged Deutsches Museum team and also King's College London in furthering investigation on the public. And yes, this is absolutely interesting, and I am really happy to work with amazing institutes here. Me, on my side, at my scale, my artist scale, I like proactive formats where I can, involve with students and perhaps create events and talks, and that's where my work happens mostly. But yeah, this also observing how people might react, and how if it would be interesting to know if you have a neutralized form of disinformation, can you actually manage then after when you're in the wild social network area?
Great, thank you. Elsa, I might turn to you. Is there any question in the lectures theatre that you want to bring up to us? There was another question for Erika, which I think Erika has answered already. But Elsa, let us know if there's a question on site from you. No?
Yeah. There was
another question for Erika, which I think Erika has answered already.
There was another question.
Elsa, let us know if there's a question on site from you.
There was another question for Erika. Did you see it in the chat?
Yes, she's answered it already, but I can ask it again. So, Erika, and I think that applies to all of you, there was a question related to the importance to recognize where deforestation happened, but also why it's happening and for whom it's happening. So, the understanding the data, whether it's, studying the sort of penguin populations or looking at deforestation, the scientific accumulating that knowledge and that data is great, but understanding why it's happening, how does that inform how you conduct your experiment?
Yeah, that is an essential part, because deforestation actually a socioeconomic process, the end result of that process. I was talking about ecological metrics and impact, but the drivers are socioeconomic, and they may be direct or indirect. For example, demand from beef from Europe may increase deforestation for pasture in the Amazon. Demand of gold in the UK is actually causing an increase of deforestation for gold mining in the Amazon. So those are the indirect drivers. So it's the demand. The direct driver of deforestation is gold mining, pasture creation, etc. That's an essential question that the audience just asked. This is crucial. But this is not done by ecologists like me. I don't have the training. It's done by social scientists and anthropologists, but it's an essential, vital part of work.
So when you set up your research projects, you look at, okay, well, we need to understand better, where deforestation happens, because we need to address these issues, or we need to understand better the impact of climate change on, the melting of ice, and, where penguin will disappear. I mean, I think some of the data you showed, Shridhar, was really, really scary in terms of the population decline of the penguins, for instance. So you're saying that this is very much part of the rationale of why and how you apply for funding to conduct this research as well.
Yeah, I think the reasons or the studies, there are different kinds of studies going on. So one of the rationale is to exactly monitor or count the penguins. It was the first rationale, because it was never happened before 2012, and then this is why now it's getting popular to count them using the satellites. So this is important. It's more of the monitoring program. And then when you have the numbers, and then you can see that if it is declining, and then you try to find out what are the reasons and why, how to monitor these reasons, and what will be the scenario in the end of the century. So these are the rationales behind the fundings.
Great, thank you. I think on that note, I'm afraid we're going to have to conclude, because time gets by very quickly. I would like to say a really, really big thank you to our three speakers again. A very big thank you to Elsa, who's been here in the background, producing and curating this program, but also supporting this. A big thank you to the whole tech team. I know there's quite a few people involved, again, hidden in the heather behind to make this happen. And just to make an announcement for next week. So next Tuesday, we have another talk again at 5:30. And the focus will be on planetary perspectives on digital technologies. We will have with us a philosopher, Reza Negarestani, who's written fascinating work on the philosophical dimensions of digital technologies. And we will have Dr. Betty Marenko, who leads the Critical Studies in Product Design program here at Central St. Martin's. And she'll talk about her recent work on hybrid animism, planetary computation, and techno-digital ecologies. So if you haven't booked yet, please book for this. Again, a big thank you to our speakers. Fascinating work, and I thought it was very complimentary to hear each of your perspectives and your use of digital tech to showcase and demonstrate the impact of ecological challenges or the denial of climate change. Thank you so much again for making the time. Thank you to the audience for being here. And we'll see you again in a week's time.
Thank you, everyone. Thank you so much, Carol. Thank you, Carol. Thank you, Elsa.